how much information can a black hole store?
Okay. Well, as much information, that's a great question. That has been a very productive line of thought. And the answer to that question goes back to Hawking and Penrose. So you could even ask another question, which is how much information can anything store?
So actually, can we back up? Why do we, like, it is actually notable that this is a question we ask of black holes in particular. Like, how often do we ask, like, how much information can the sun store? Like, why in particular are we interested in how much information a black hole can store?
Well, it turns out that that's been an incredibly productive line of thought, A. And B, it also turns out that that is the main fact that we're most confident about quantum gravity. So the two great theories of 20th century physics, gravity, Einstein's theory of the curvature of space-time, and gravity and all the rest of it, tends to make itself felt at the very large scale. And on the other hand, quantum mechanics, a theory of the very small, to do with Heisenberg's uncertainty principles and atom and atomic spectra, tends to make itself seen at the very small scale. These are the two most beautiful theories of 20th century physics, the two things that we should be most proud about that we discovered in the early 20th century. And it was noticed pretty early on that these two theories seem to be inconsistent with each other. That the most obvious ways to try and reconcile quantum mechanics and gravity break. You can't really shove them together. And this is a problem if you think that the world should be comprehensible, that there should be some theory that in fact is consistent that describes the world. So this has been a big project in theoretical physics over the last few decades, is trying to understand how we can take Einstein's general relativity and quantum mechanics and make them meld together in a mathematically and physically consistent manner. It's tricky in part because there's very little experimental guidance, because general relativity tends to make itself felt at large scales, quantum mechanics at small scales, and so trying to find a place where they meet in the middle, and it must be that they do meet, but that trying to drag that out with experiment is very tricky. But this has been a big project, is trying to figure out how to do this. Einstein spent some years unsuccessfully doing this in the later, less productive part of his career. And this project of trying to unite these is something that a lot of people have thought a lot about. The string theory comes out of this project, a number of other lines of thought. There is, however, one fact about that merger that we are most confident about anything about the merger, and that exactly returns to this question of how much information can you store in a given region of space-time. And in fact, how much region, and the answer to that involves black holes. So the answer is how much, if you have a region of a certain area, maybe a sphere of a certain area, and you said how much information can you store in that region, the amount of information you can store, measured in bits, the entropy of that region, is given by the area of that region, divided by G, Newton's constant, and h bar, Planck's constant. So that's how you know that this is something to do with quantum gravity, because it involves both G and h bar.
Is that the only situation in physics where both of those constants end up being in the same place?
That is not the only situation. No. Anytime you have quantum gravity, they'll tend to be in the same place. And sometimes even when you don't have quantum gravity, but you have the interplay of gravitational forces and quantum degeneracy pressures, that'll end up in those. But it's in some sense the simplest situation in which it occurs, which is why so much time has been spent thinking about thought experiments to do with black holes.
Right.
So there was a physicist called Bekenstein who figured out that should be the answer, the area divided by G/h bar. And then Hawking's great contribution to physics was figuring out that it was the area divided by G/h bar, but he also got the prefactor, and the prefactor was a quarter. So this is Hawking figured out that it's a quarter. It's the area divided by 4 G/h bar. And this is a super interesting answer. How much information can you store in a given region is given by the area. And in fact, black holes maximize that. Black holes store that amount of information in a given area.
And specifically area meaning surface area.
Meaning surface area,
yes.
Exactly. So the reason that that's such a wild answer, and an answer that's led to all sorts of thought experiments to do with quantum gravity ever since then, is that you might naively think that the amount of information you can store in a region is given not by its surface area, but by its volume. So if I have a hard drive and I take another hard drive and another hard drive and another hard drive, and I keep piling them up, the amount of information I can store on those hard drives scales like the number of those hard drives. And that means it scales like the volume of the region in which I'm storing the hard drives. That everything we know about classic thermodynamics tells us that the amount of information should scale like the volume. Everything we know about non-gravitational physics tends to tell us to point in the direction of the amount of information you can store goes like the volume. And yet, this is like the most surprising fact that is incredibly generative, is that once you add gravity to the picture, once you combine quantum mechanics and gravity, the amount of information you can store in a given region, a given sphere, goes like the surface area of that region, not like the volume of that region. And you might think that that's can't possibly be right. And you might give the following argument. Okay, so there's some region, and I'm just going to keep adding more and more hard drives to that region. And as I make that region bigger and bigger and bigger, the amount of information on those hard drives scales like the number of those hard drives, which goes like the radius of that region cubed. And the thing about the radius of the region cubed is it grows faster at large radius than the radius of that region squared. So I just told you that the amount of information you can store in a region is given by the surface area. And yet I also gave you a way to make it scale like the volume. So eventually, if I make the region big enough, the amount of information in that volume will be bigger than the bound that I just said. Therefore, I've ruled out Hawking's and Penrose and Bekenstein's bound. What goes wrong with that thought experiment is that eventually, if I make a big enough pile of hard drives, the whole pile of hard drives will undergo gravitational collapse and form a black hole.
Actually, but then there has to be sort of not experimental, but a sort of do you have to crunch the numbers then to determine that just before the pile of hard drives would collapse into a black hole, the amount of information stored in that cubic pile of hard drives is less than the amount of information that then gets turned into the surface area of the black hole? Because theoretically, it's if I don't know if I'm like getting my math intuitions right? It's like theoretically possible that like even though the black hole is smaller because it's only the surface area, the cubic ends up being bigger.
Yeah, you have to run that calculation. But if you do run the calculation, it turns out that it's nowhere near. When it wasn't close.
Okay. It's not one of the things where they just balance each other out.
Yeah, they don't just balance each other out. If I take an online shopping website and I buy a bunch of Western Digital hard drives and I calculate the information storage capacity of those and compare it to the area of a black hole, I figure out when the pressure in the hard drive will be enough to stop it collapsing to form a black hole. It is nowhere close. It will make a black hole way, way, way before it comes close to violating Bekenstein-Hawking bound.
Got it. Okay. Sorry, I didn't mean, and then you...
Oh, yeah. So that's the information storage in black holes. The reason you know that that's also the information storage bound for anything, not just black holes, is that if you had something that wasn't a black hole that had more information than that in a given region, and you just added matter, eventually that thing itself would collapse to form a black hole. And so it couldn't be the case, just logically, that that had more information than the black hole it'll tend to.
You just hinted at the idea that somehow this is like the most productive line of thought that physics has come up with in the last few decades. Why is that? Why is the fact that the area is proportional to the information of a black hole tell us so much about the universe?
It's been extremely important for our understanding of quantum gravity. It's perhaps the central fact that we know about quantum gravity is that the information scales with the area. And that is a hint. That fact that was known since the 70s was a big hint that became very influential later on. As understood by Bekenstein and Hawking, it's just a weird fact about black holes, perhaps. But we now understand it as a strong indication of what we call the holographic principle. The holographic principle has been a sort of powerful idea in quantum gravity, and it's the following. So if you took a non-gravitational system, like in which you ignored gravity, like the pile of hard drives, the information storage would scale like the volume, as we discussed, whereas in fact it scales like the area. So, or another way to say that is if you take a 3 plus 1 dimensional theory in which you have both quantum mechanics and gravity, that the information storage scales like r squared rather than r cubed, i.e. it scales as though you had a non-gravitational system in one fewer dimension. So if you had a 2-dimensional theory in which there was no gravity, the information stored in a given region would also scale like r squared, because the information would be just the 2-dimensional volume, as in the area. So in other words, it's, at least as far as information density, the information capacity is concerned, a gravitational theory in 3 dimensions is like a non-gravitational theory in 2 dimensions. Or more generally, a gravitational theory in n dimensions is like a non-gravitational theory in in n-1 dimensions. So that is a big hint that forms the basis of the holographic principle. It's like gravity eats information. Like there's less information than you thought there was, that you naively thought there was, if you didn't include information. And so the holographic principle says that maybe that's not just a neat observation. Maybe it in fact is the case that for some quantum gravitational theories, there is another theory that is exactly equivalent to it in one fewer dimension. And so this led to Maldasena's ADS-CFT correspondence, the gauge gravity duality, which was the most cited paper in high-energy theoretical physics ever, I think, maybe at this stage. And in the late 90s, he wrote down, he took that as a hint and it wrote down we believe, an exact duality between a particular theory of quantum gravity, some particular flavor of string theory, and a non-gravitational theory that lives on the boundary of that space.
And what problem does it solve if you can model the world in a fewer dimension that doesn't involve gravity?
Well, so this was a very influential paper, as I said, and really becomes a tremendous theoretical laboratory for trying to understand the connection between gravity and quantum mechanics. One problem it solves is gravity is mysterious, particularly once we include quantum mechanics in various ways that we could go into. This is why it's hard to quantize gravity. But if you can say that this theory of that involves both quantum mechanics and gravity is exactly dual, is in some sense the same theory, as just an alternative description of a theory in one fewer dimensions that doesn't involve gravity, well, that's great, because we have much better grasp on how to understand theories that don't have gravity than we do on theories that do have gravity. So it puts everything on a much clearer footing to have this non-gravitational description, because then you can just use the standard tools of non-gravitational quantum field theory in order to define it and understand it.
So at one level, I understand that if the information in a area is limited by the information that would be on the surface of a black hole in that region, then you can model the surface area as a two-dimensional object. On the other hand, if I just think about like real world, it's just like you're over there and I'm over here, and if I like do something here, it's not interacting with you. And in order to model that fact, I need to model the dimension in which the third dimension in which we're separated, which I guess if I'm like actually looking at you through a window pane, I maybe wouldn't have access to. So, and so how in 2 dimensions, how do you model how like that? There's a reason we have the third dimension, right? And how is that modeled if you reduce that dimension?
Yeah, so maybe I should just lead with some disappointing news, which is that ADS-CFT was a tremendous conceptual breakthrough in our understanding of quantum gravity and embodied the holographic principle.
Yeah.
But at the same time, it doesn't describe our universe. In particular, in ADS-CFT, there is a negative cosmological constant in the gravitational theory, and our universe, as we discussed before, has a positive cosmological constant. So it's great because it provides an existence proof of a well-defined theory of quantum gravity, not, alas, in the universe in which we live in. Okay, but having said that, yeah, it's extremely confusing and was a very impressive result, precisely because you might think, how could it possibly be the case that 2 different theories in 2 different dimensions could turn out to be equivalent? And the answer to your question is, if you have two people who are living in this negatively curved space and talking to each other, what does that look like in this other theory? I say that there's this process going on in the gravitational theory that's dual, which is exactly isomorphic to some process going on in the non-gravitational theory in one fewer dimensions. But what maybe looks very simple in one theory, like you and I chatting back and forth to each other, would look like some complicated plasma physics in the lower dimensional boundary theory. And so the sort of complexity of how it looks like, which is a better description, does not need to be conserved across the isomorphism. So, in fact, that's often what we use it for. We use it to do arbitrage between things that look simple in one theory and things that look simple in the alternative description. And we use the fact that things look simple in one to understand the sort of complicated version in the other. In fact, it flows in both directions. You might naively expect that because gravity is so complicated, we would always be using the non-gravitational theory to understand the gravitational theory. That's not always true. There are these plasma physics is itself extremely complicated, and there are these big collisions that we do at RHIC in Brookhaven, where we smash two gold atoms together and make big fireballs of quark-gluon plasma. And it's extremely challenging to calculate what would happen there. And yet people use this duality in the opposite direction to say, even though it looks super complicated with this weird plasma physics in the non-gravitational theory, it's actually can simply be understood as some simple black hole property in the gravitational theory.
Would any, maybe not ADS-CFT itself, but would some theory which relies on the holographic principle ever be able to account for a world like ours where, unlike the surface of a black hole, there isn't a boundary because of the positive cosmological constant and it's constantly expanding? Is there some hope that there, in fact, is a way to have some sort of dual theory to this that somehow describes a boundary? Or
yeah, people are working on that. Okay. That is an open area of research. Ever since the original ADS-CFT was written down, people have been trying to formulate versions of it in which have a positive cosmological constant. It's difficult, and part of the difficulty goes all the way back to Archimedes. You need it is easiest to formulate a theory if you have a fixed point on which to stand and observe things from a distance. In a universe with a positive cosmological constant, that you don't have that. You're necessarily mixed up with the system.
Yeah.
Because you live in a universe that has only a finite amount of entropy, a finite amount of free energy, there is inherent limitation to the precision of the experiments you can do. That just makes things way trickier. So for that and related reasons, it's a much harder project, but for sure, people are working on that.
What is the correct conceptual way to think about this? Because one version is the boundary is one way to simplify the processes that are actually four-dimensional. Another is, I don't know how we think about this in the context of black holes, but maybe in the context of black holes, no, the information actually is on the horizon. The analogous thing here would be like, no, somehow we are on the boundary of the universe somehow. Is there a sense in which one of these interpretations is correct?
Yeah, okay, that's a good question. So this duality idea where you have two different descriptions of the same thing is not, the ADS-CFT was not the first such example in physics. It's a common trope in physics that you can have two different descriptions of the same thing, some of which are more useful in one scenario, some of which are more useful in the other scenario, but which are both exactly correct. And there are non-gravitational examples in physics that go back a long way. You may then ask, which one is right and which one is not right. Is it actually a CFT that's pretending to be, that has this weird alternative description as a gravitational theory, or is the gravitational theory correct and the other one's not correct? I think this is more of a philosophical question. My answer would be if the isomorphism was just an approximation, like it was really one thing and you were just pretending it was the other thing, and that approximation worked in some region of validity and not others, then I would say that the one was right and the other one was just a alternative fanciful description. That is not our understanding of ADS-CFT as we understand it today. Our understanding is that this is a precise isomorphism. It's not a analogy, it's not a metaphor, it is not a approximation that is valid in some domain and not another. It really is the case that these two theories are exactly equivalent to each other. And if that's correct, then as a matter of philosophy, I would say those are both equally real. It's not the case that one is more real than the other. They're perfect simulations of each other. Are you an ADS dreaming you're a CFT, or a CFT dreaming you're an ADS? I think these are just two completely different, inequivalent descriptions of the same identical physics.
Tell me if this is just like a question that just doesn't make sense, because look, when I was like, if you try to ask somebody about like the quantum many worlds, where are the other worlds, right? And they're just like, it's just like they're in Hilbert space. And like, where is Hilbert space? And they're just like, no, dude, it's just like a conceptual, like you don't, just like stop asking questions. Intuitively, it feels like there should be a sense in which like there's some physical existence, and either that existence is in this 4-dimensional space, or it's in some space that exists on the boundary. Is this just, again, just going to lead us into philosophical loops, or is there something that can be said more about it? And also, in a world like ours, what exactly would the boundary mean?
Yeah. So there are two components to that question. You have an intuition that if something is real, it needs to be spatially localized, and things that are delocalized in space somehow can't be real. I would say that that's not my intuition. My intuition is that there can be two completely different descriptions of the same physics. And if it's precise, neither of those is any more real than the other. Things do not need to be spatially localized. You separately asked, what would it look like? What would a version of where is the boundary theory in de Sitter space, since there's no boundary? That is a great question that people who are trying to generalize ADS CFT to a universe like ours that has a positive cosmological constant, that they wrestle with. And there's more than one proposal, some of which is that one example of a proposal is that the dual theory should live on the cosmic horizon. So if you go 5 billion light years, you can send information to that point and have it returned to you. But on the other hand, there are things that are 100 billion light years away that we'll never be able to communicate with. And there's a boundary between those two, between some things that we could in principle communicate with and things that we couldn't in principle communicate with. That is the cosmological horizon. And some people who are trying to do a version of holography that works in universes with a positive cosmological constant like to put the second theory there. Other people like to put it in the distant future, in the sort of infinitely distant future. And that's part of the problem, is that where do we even put that theory? It's not like in our universe where you can just put it spatially infinitely far away and be done with it.
If it's spatially finite, then we are currently at the boundary of infinite many other universes that are located or whose center is located elsewhere.
Absolutely. So a cosmological horizon is very different from a black hole horizon in this regard. A black hole horizon, there is a point of no return. And if you get closer than that, you fall into the black hole and you're never getting out again. And everybody can agree where that is. For cosmology, there is a point of no return, but the point of no return is returned to a given person. And so for each person, there is a different point of no return. Right. And as you say, we live on the boundary just as much as we live on the boundary of those people live on our cosmological horizon, we may live on theirs.